morning. First, let me know whether you're able to see this screen.
Yes,
Yes. Okay. Thank you. Okay. So far we are discussing cache memory in this model 4, and we have discussed how to read cache. We have different techniques like direct mapped cache or set associative, fully associative, and how to write the data into the cache. We have write through policy, write back policy. So we discussed in detail and how the cache is constructed, what is called tag field, what is called valid bit, and what is called data field, and how the address is translated into cache address to get the data from cache. So we discussed in detail. So now let me move from cache. So now we are going to discuss about a new concept called virtual memory. Okay, so we are going to discuss virtual memory. Yeah, please mute your mic. Virtual memory. Right. So before we get into that, let us try to understand the organization, memory organization again, so that it will be easy to get into the topic. So we know we have levels of memory. We have a CPU and we have a cache memory of smaller size. Then we have a somewhat bigger main memory. Then we have a disk memory which is largest in size in the memory system. So this is the disk memory. Okay, hard disk. Okay, a disk memory. Right. Now there is a connection between all the memory to CPU. Okay, right. So when CPU looks for something, and first it checks whether it is there here. Then if something is there, then it's called cache hit. Otherwise cache miss. Then it has to go to main memory. And in the main memory, if the data is there, then it's called hit in main memory. From now onwards, we will call hit in main memory is something like uh, uh, here we are talking about blocks, right? There are blocks of data in cache, right? So here we have to talk. Now we have to, from now onwards, we have to talk. We are going to concentrate these two, right? So now we are going to use a term called pages. So main memory has some fixed pages. There are some pages, and whatever the information is looking for, it is available in the main memory. Then it's called page success. Otherwise, page fault. Okay, then it is getting into disk memory. And if that record information is available in disk memory, it's fine. Otherwise, it has to go to secondary memory. If even that information is not in the secondary memory, then it's overall a new data the CPU is looking for. It won't occur, but in general, I'm talking. It's an overall new thing the CPU is looking for. So the new thing has to be stored by the programmer in disk memory. Okay, right. Now let us try to focus our attention on this one. So what's happening here? Usually, uh, uh, we feel that the system memory means disk memory, because the disk memory size is depends on number of address lines the CPU is having. Okay, so accordingly disk memory is selected, and these memory are selected according to the availability and affordability. So whether it's affordable to go with that capacity or not, based on that we are selecting these. But usually this will be selected based on the addressing capability of the CPU, right? Fine. Now the thing is, when CPU is accessing something from the disk memory, it's a time consuming process. Okay, so it will take some milliseconds of delay, some milliseconds of delay to get something from the disk memory. Whereas the same, it's something from cache memory or main memory, it will be in nanoseconds. It will be in nanoseconds. Okay, some variation. maybe nanoseconds, microseconds, something like that we can take. So let it be nanosecond, and this usually will be nanoseconds or close to microseconds, but definitely getting something from the disk memories in terms of milliseconds. Okay, right. Now, now the thing is, originally what happens is we users are thinking about the size of this memory, and we are writing program according to this size. Okay, suppose this is the 1 gigabyte capacity, then we are thinking that we can write a program of close to 1 gigabyte so that we can process in our system. So we are writing usually, but it is a headache of the designer. We are programmers, designers, or it is a headache of operating system to to uh, to to make it comfortable. Means it will transfer the program into main memory and cache memory such that CPU can execute the things in fast. So this is what the idea. Okay, right. Now let us take one concept. Suppose we have written a single program with multiple portions, with multiple mutually exclusive, mutually exclusive portions. We have written a single program, but there are some mutually exclusive portions. Okay, in that case, so this program is in disk memory. Okay, so this is stored in disk memory. Now, from this, a portion of, because the portions are mutually exclusive, right? At a time, a portion of memory will come to or a portion of program will come to main memory. From that, a portion will come to cache memory. From that, one instruction will go to CPU. I repeat again, we, from user point of view, we are thinking of this capacity and we are writing a program. Suppose the program is like this, a single program with mutually exclusive portions. Then that individual portions, portion by portion, will be shifted here, and whenever CPU is looking for that, it will be checked whether it is available in that portion. If it is available, then at microseconds or at nanoseconds speed, it can get the data and it will execute. So from that portion, some portion of that portion of a portion will be shifted to cache. From that, it will be shifted to CPU. So this is the way it's working. Now, this concept, writing a single large program with multiple mutually exclusive portion, is usually called as memory overlay. Memory overlay. Okay, I stop at this point. Please let me know whether you are getting what I'm talking. If you are not able to understand what I'm talking, please let me know. I will clarify again. Point. A single program. Let us take, there are cases. Case number one, we are discussing like this. Single program. There are multiple mutually exclusive portions are there. Then some portions will be shifted here. From that, some portion will be shifted here. Then CPU, whenever it look for something, it will first check whether it is available within that part of that portion, or within that portions, or it is available in the program. So like that it will check. Okay, so this way of writing a program is called as memory overlay. Mutually exclusive portions, memory overlay. Anybody having any problem in understanding this? If you have any issues, please let me know. I'll clarify. Okay, right. Then let us go to the second concept. So rather writing single program, your user can write multiple programs. multiple programs, and these multiple programs are stored in disk memory. From this, one program can be shifted to main program. There are multiple programs, right? At a time, one program will be shifted to main memory. Then, in that portion of that program will be shifted to cache. Then, that's the way the things are organized. So, there are possibilities. One would have written a single program, or one would have written multiple programs. Only two possibilities. Suppose single program, there is no mutually exclusive, then it will be treated like a multiple programs. So the operating system itself will divide that program into some portions, and portion by portion it will shift. So we need not to worry on those, because our duty is we are trying to code, that's all we have to execute. But internally it is the job of design engineer to design how to divide that program and how to shift in the subsequent hierarchy. So that is the headache of designer, not ours. Okay, right. So what I'm trying to say, we have a program here, and portion of the program will be occupied. Okay, and now how this is happening between these two. This is what we are going to discuss. Already we discussed how the shift is happening between these two: direct mapping, set associative, fully associative. There are the concepts used to map content of this to content of this, that we discussed already, right? Now we are going to discuss how the transfer is happening between these two. Okay, so this is what virtual memory concept. Okay. Now let us go to the topic, proper virtual memory topic. So we know, according to Moore's law, year by year or once in 2 years, the number of pins or number of transistors in the integrated circuit gets multiplied, doubled, right? So every 2 years, the number of transistors inside the chip gets doubled. This is what Moore's law prediction. We have discussed already in the first module. Now let us bring that law here. If number of transistors are doubled or number of digital components are doubled in the IC, it indirectly means number of pins are increases. So over a period of time, the CPU capacity increases. The number of transistors in the CPU gets increases. It's increasing. Due to that, what happens? Since the capacity increases, which leads to increasing number of pins. The number of pins are increasing. So every single pin we get new in the CPU in the form of address pin, then it has the capability of accessing 2 to the power n capacity. For example, let us take one simple example. Suppose a CPU has 8 address pins. 8 address pins. Then 2 power 8 addresses it can generate. So this we know, right? So 256. Suppose due to Moore's law, the number of transistors in the chip got increased, and indirectly it means we are increasing number of pins in the CPU, and especially the number of address pins is, just for example, usually it will go in even numbers. Just for explanation sake, let me take 100 pins. Then what will happen? It will become 2 power 9. So 2 power 9 is what? Double, right? It means what? The same CPU, earlier we used 256 locations memory. Now we have the freedom to use 512 locations memory. It means every single pin will lead to accessing capacity increases. Okay, so that's why nowadays we are able to connect more number of memory with the system. Okay, now let us come to the point. This memory, I mean disk memory. If CPU number of pins increases, then naturally we would like to have larger capacity of disk memory. We would like to have larger capacity of disk memory. we usually we like that, right? We want to have a larger capacity of memory in our system. Fine. If this is larger, then from user point of view it's okay, but from performance point of view there is no use of increasing this size. We want to increase this size, right? Because this is the fastest memory. We want to increase the cache memory. This is the fastest memory. We want to increase the main memory. This is the fast memory compared to this. But unfortunately, if we increase this one, then what will happen? The overall cost of the system will become increased. Suppose the cost of a computer is 25,000, then if you increase the memory size, then it may go to 30,000, something like that. So now the challenge is, this is unavoidable. Year by year, or once in 2 years, or once in a decade, the number of pins are getting increased, and it means that CPU can access more memory than it was designed initially. Memory means this memory only, because this is the one we able to interact. Okay, but increasing of this may be good to store large data, but execution point of view, by keeping the same size of main memory but increasing this one, no use. So if we want to increase this size, then this will increase the cost of the overall system. So we don't want to spend more on this one, but we want to get the benefit of in enhanced disk memory. What to do? Now the idea of virtual memory has come. We are going to use virtual memory concept to manage this issue. Okay, so I'll stop again for a minute. Please let me know whether you are getting the point. Why we need what is called virtual memory? Why we need virtual memory? The accessing capacity of CPU is increasing over a period of time. It means it can accommodate larger size of disk memory. If larger size of disk memory is there, it is good to store larger data, but performance point of view, it won't add value to the system. So we want to increase the performance point of view. So we have to increase the main memory. We have to increase the cache memory according to the size of new increased size of disk memory. Then only we able to get the same performance. But unfortunately, the cost and the size of these memories, like cache memory, main memory, they're all large. They occupy more space and they are costly. So how to manage this issue? This is the idea for virtual memory. Are you all clear?
Yes,
Now, yeah. Now let us go to the discussion. So the point is that number of pins, in number of pins I mean address pins. Okay, there are even in other pins also added, but our intention is only we are bothering about address pins. Number of address pins are increased, then the addressing capacity of main CPU will increase. Now what we are going to do, it is the designer point of view I am talking. What the designer is going to do, he is going to use the increased address, and is going to manage with the smaller main memory, whatever it is having, whatever it is there in the system, with the normal size of main memory, the designer has to manage this increased addressing capacity of CPU. It means virtually it is believed that the main memory is also increased according to this capacity. Physically it is not increased, virtually. Virtually means what? It's like not seen, right? So virtually it is increased to meet the addressing capacity of CPU. This is the idea of virtual memory. Okay, right. That's why it's called virtual memory. We are not going to increase the size of main memory, but we would like to treat with some concepts. We would like to treat that main memory is increased virtually, not physically. That's why it's the virtual memory. Some examples with some how it is possible that we will understand. Now, for virtual memory, we should know the main memory, and disk memory or physical memory. Physical memory means disk memory. The main memory and disk memory are divided into pages. Or divided into pages. Into pages. The pages are fixed in size. Fixed in size. For example, let us take, just for example, explanation sake, let us take, let 1 megabyte of disk memory and 64 kilobyte of main memory. Originally, this will be in megabytes, this will be in gigabytes. Just for understanding sake, let me take this. Okay, now and page size of 4 kilobyte. Page size of 4 kilobyte. Okay, now for this, what's happening is this is 1 megabyte of disk memory. It is divided into pages. Similarly, we have 64 kilobit of 64 KB. This is 1 megabyte. So it is also divided into pages. Suppose the page size is 1 KB, 4 KB, then here also the page size must be 4 KB, here also the page size must be 4 KB. So that's the idea. Okay. In that case, how many 4 KBs are there in the 16? 15 4 KBs, right? So 0 to 15. So each size will be 4 KB. Similarly, here that 1 megabyte is divided, right? So we need 256 partitions, and again each page size of 4 KB. Right? Now, let us assume this is the enhanced capacity. Because of number of pins increase in CPU, this has got increased to 1 megabyte. But we are not able to increase this to 1 megabyte. This will lead to costly system. So that's why we are managing it already existing 64 KB. Let us assume. Then let us draw the addressing thing. So this is the address from the CPU. So for 1 megabyte, we need 20 address lanes. We need 20 address lanes. For 64 KB, 1 megabyte, we need 20 address lanes. For 64 KB, we need 16 address lanes. So please remember. Okay, so 0 to 19. Okay, right. So for 4 kilobyte, 2 power n is equal to 4k. It means n is equal to 2 power 10 is 1k, 2 power 11 is 2k, 2 power 12 n is equal to 12. Okay, so every page, this is the page, this is the page. So there are locations in page. How many locations? 4 kilobyte. Okay, right. Now this is the address from the CPU. This is the address from the CPU. In this, what we are doing is we are alerting 0 to 11, 12 bits, 12 bits for the pages. Within the page, there are 4 kilobit locations, right? To access that, we are using 12. So remaining 8 bits, remaining 8 bits are used to select which page. Okay, clear? Now let us take this one. Uh, what is called main memory. So main memory is 16 address lines, 0 to 15, and in this again we are using 12 bits because the same page size, right? So this is the main memory, and this is 0 to 11, 12 to 15. So there are 4 bits. So these 4 bits are used to, okay, this 8 bits are tells that which of 256. This 4 will tell us which of 16. This point is clear. So please tell me whether you are able to understand this.
Uh,
Any doubt? Any problem, pa?
like earlier we had that block of to tell that within each block of each
It's
byte
not
we
block,
get it.
pages,
So
pa, pages.
yes, so here similarly there is nothing like that block.
I'm not getting. You are asking how do I say 16, right?
Like
How do
the
I?
12 bit these are that these 12 are to select one of the these 4K
No,
pages.
yeah, I'll tell you. I'll tell you. So there are 16 pages, Napa. Is there any doubt in that? There are 16 pages. Is there any doubt? Because in the problem it is given 4 KB. Page size is 4 KB. Available 64 KB divided with 4 KB. We will get 16 pages. Okay, pa? This is a page 0, page 1, page 15. This is the case of main memory. Okay. Now every page will have 4 kilobyte of size, right? Every page will have 4 kilobyte of size. I told you initially, whenever memory accessing memory means byte level access. Byte level access. So how many bytes are there in the 4 kilobyte? 4000 bytes are there, right? Okay, Opa?
Yes,
Right? Now,
yes,
now this first 4 bits. Okay, let me take one example so that you will understand clearly. Suppose I mean 000 here, 00 here. So it means where it will take me? It will take me this page. Which of 16? Okay. Suppose it is 1111. Where it will take me? It will take me to this page. Clear up? So these 4 bits decides which of the 16 pages in the main memory. Okay, right? Within the page we have 4 kilobyte. At a time we can access only one location of the page. So this 12 bits decides which one of this, which one of this 4 kilobyte. Okay, that's called page offset. This is called as page offset. Within the page, 4,000 locations are there. So which of these 4,000 locations we can access? That information we can get it from there. I hope now I clarified the point. Is it okay, Pa? The
Yes,
same,
sir, yes.
yeah,
Thank you.
yeah. The same explanation goes here. So there are 256 pages in the disk memory. So this tells that which of the 256, and every page of 4 kilobytes. So which location in that particular page. Okay, so that's what the right now. So this is the way the designer first will see how many bits mean, how many pages are divided, and accordingly how many bits are needed to access the page, how many bits are needed to access within the page, so that the designer should calculate. After that, the designer should prepare a table. The table contains, table means what? It has a rows and columns, right? So the designer, it's the designer's job, it's not our job. We are programmers, it's not our job, but we are understanding how the virtual memory concept is taking place. Okay, so they are creating a table. Table means we know there are rows and columns. So how many rows are there? That depends on how many pages are there in the disk memory. How many rows in the table depends on how many pages. So in this case, 256 pages. So 0 to 255. 256 pages of disk memory. Okay, right. Now, how many columns? That depends on how many number of bits are used. How many number of bits are used here? 4 bits. So that many columns. So 1, 2, 3, 4. 1, 2, 3, 4. So 4 bits. It is based on number of bits used in this. So one table is created with number of rows are equivalent to number of pages in the disk memory. Number of columns are equivalent to number of bits needed to access which of the page in the main memory. So that many bits are used. Then one extra bit is there, no? This bit they are calling it as present bit. An extra bit is called as one bit. They are calling as present bit. Okay, right. Now, what is this table? This table is named as page table. The name of the table is page table. So this page table contains 256 rows because 256 pages are there in the main memory, and 5 columns. In that 4 columns, because there are 16 pages, we need 4 bits to access any of the 16, and then one present bit. Okay, at a time in this, any 16 entry you can find. So the table will have 16 entries. Okay, the table filled with 16 entries, and here, for example, let me redraw again. Let me redraw again for you to understand. So 8 bits, right? 8 bits, 12 bits. Let me redraw again. Look here. Listen carefully. Very interesting. So here we will have some combinations. Okay. So let me take one simple combination. Let me take simple combination. 0, 0, 0, 0, 4 zeros, 1. Okay. So this is the combination available here. So this is this is referring to this is referring to this, is it or not? This is referring to this, agree? This combination is referring to this place. Okay, right? Now in that, suppose the entry is something like this. Now what will happen? This information, this this information is copied here. This information will be copied here. Now this is the entry will become this one. Since something is valid, no, the present bit will be 1. Okay, 1. Now this is the address generated by the CPU. This is the address generated by the CPU. Now from this, the first 8 bits are getting into the page table of this location, because the entry 1, that's why here it goes. In that, it will read what is the information contains in that place, that will be mapped here. So it means it has to go to 8th page, right? It has to go to 8th page of the main memory. In that 8th page, which byte we want, that information, these two are equally mapped. This is mapped, this is copied here. This information will be copied. 12 bits are equal. They will be copied here. So this will go to this location of the main memory, and it will read that page with this particular location in that page. This point is clear? This point is clear? Please
Yes.
answer me. Very easy. So what the designer has done, he has created one table, and for that he has used how many, and for that what he has done is he has divided main memory and disk memory into pages. That number of pages information he has used to construct the table, and the table is called as page table. So using the page table, we are able to map the generated new address of CPU. New address means what? Number of pins are increased in the CPU. So the new address being generated, this new address is somehow mapped with the existing main memory capacity. Okay, right. Suppose, let us assume, one more case. Suppose it is generating something. Suppose it is pointing something here. If the entry is not there, the present bit is 0. Let us assume. If present bit is 0, it means what? That particular page is not available in the main memory. So this is like catch miss, right? Like that here, page fault. See, always we cannot expect all the pages are available. There are possibilities. Some pages may not be available initially. Initially, when the main memory started building, like cache memory, how it was built, like main memories also started building, right? Once the computer is turned on. So initially, there may be a chances that the particular address may not have some information. Initially, at the starting itself, it is generating this address. So at the starting, nothing will be there in that, right? Because they're all RAM, nothing is there. So this leads to page miss. So now we can call it as page fault. Page fault. So page fault can be minimized or may be minimized once the computer started running after some time. After some time, the page table will be get filled, and after that, the page success will happen. Page fault will be minimum. So this is the idea of virtual memory. Okay. Now, can you answer me? What will happen if I increase the, I mean, if I reduce the page size from 4 kilobyte to 1 kilobyte? What will happen?
So number of pages in the main memory will decrease.
Number of pages not only in the main memory but also
So
in the
disk
disk memory.
is
So
overall.
this leads to what? This leads to what? If both
So
are
less number
increasing.
of
Yeah,
storage
No,
locations.
yeah,
page table entry will be increasing, right? Agripa?
yes,
This will increase the size of the page table, is it or not? Page table size depends on what? How many pages are there in the main memory, how many pages are there in the disk memory, right? So the table size will be increased. So the page table size is depends on how many pages are used in the system, in the main memory as well as in the disk memory. Accordingly, the size of the page table will vary. Okay, one point. So let me conclude these points. If page is there, if the particular page is available in page table, then this leads to the information retrieved from main memory at faster rate. At faster rate. Suppose the page is not available. If page is not available in page table, this leads to page fault. Page fault. And this leads to data information required or retrieved from memory, because it is not available in the main memory. So it is available in disk memory. This leads to slow. That leads to fast. This leads to slow. Okay, right. Now a question will come: where this page table is residing? Where is this page table? This page table is part of the main memory. Part of the main memory. Okay, and one more thing: how the CPU understands where the page table residing in the main memory. Okay, for that we are using a register called origin register. There is a register called origin. One register is called as origin register. This is called as, okay, origin register. This origin register contains starting address of the page table, where this page table is residing in the main memory. That information is available in origin register. This origin register is part of the CPU registers. Inside the CPU we have some registers, right? So it is part of the CPU registers. So we got introduced new terms: virtual memory, page table, page miss, page fault, page table, where the page table is residing, what is called origin register, what is the purpose of origin register, and where it is residing. Okay, so any doubt in these points? So this is the idea of virtual memory. Okay, fine. Now I'll stop at this point. So someone has sent message.